Morning.
Morning.
Not too bad. Yourself?
I'm doing good. Thank you.
All right, folks, I have 2 minutes past, so we should probably go ahead and get started. Let's see, I'm not sure if we have any points of business that we need to discuss. Homework number 2 is still out. It's nominally due on Friday. Just a reminder, I have office hours scheduled for tomorrow morning, so if you're working on the homework and you're stuck on something, please feel free to drop by and ask questions. That's the only thing on my radar. Is there anything else that we need to discuss before we dive on in for physics today? Okay, if not, then let's remind ourselves what we talked about last time. On Monday, we were discussing the addition of angular momenta. So we considered the case when you have a system that has both orbital and spin degrees of angular momentum. And we talked about how to add the two together because it's the total angular momentum J which governs the rotational properties of the system. The problem was sort of summarized in the fact that Jz can be obtained easily by adding up Lz and Sz, but J squared, which controls the magnitude of the total angular momentum, does not commute with either of the Z components separately. So you have to trade off between one basis or one picture of the physics in which you have a well-defined separate identity for the Z component of angular momentum and the Z component of spin, or a different basis which has well-defined total properties J. And we discussed how to do that. We worked one example in detail. This was the case of a spin 1 orbital angular momentum plus a spin 1/2 spin angular momentum. We said the allowed values for the L equals 1 orbital angular momentum were +1, 0, and -1. And when we add that together with the spin 1/2, the spin 1/2 can either be +1/2 or -1/2. And based on the algebra of angular momentum, we knew that the angular momentum states must come in ladders. So when I form the maximum state +1 +1/2, I get one unique +3/2 state. This must form the upper state of a ladder. That +3/2 ladder contains a total of 4 states. +3/2, +1/2, -1/2, -3/2. That uses up 4 out of the 6 dimensions we started with. The other 2 form their own separate ladder. This is an orthogonal combination of the 2 spin states, orbital angular momentum +1, spin -1/2, and orbital angular momentum 0, spin +1/2. The opposite combination that does not form this state forms instead this state. And by using that orthogonality condition, we found the new top of the ladder. And by lowering the ladder, we generated the rest of it. So this was the decomposition of angular momentum 1, spin 1/2 into one ladder of total angular momentum 3/2 and a second ladder with total angular momentum 1/2. So the final answer that we derived for all of these states, if I make a table, the states J and Jz expressed in terms of the states Lz, Sz, we found 3/2 plus 3/2 was uniquely given by +1 +1/2. 3/2 plus 1/2 was given by 1/√3 plus 1 minus 1/2 plus √2/3 0 plus 1/2. This is the combination of this angular momentum up, spin down, and this angular momentum 0, spin up that forms this state. Likewise, we had 3/2 minus 1/2 given by 1/√3 minus 1 plus 1/2 plus √2/3 0 minus 1/2. 3/2 minus 3/2 was given by the unique state -1 minus 1/2. These states constituted that 4-dimensional ladder J equals 3/2. And the other 2 states were made up of the orthogonal combinations of these 2. 1/2 plus 1/2 was given by √2/3 plus 1 minus 1/2 minus 1/√3 0 plus 1/2. And 1/2 minus 1/2 was given by -√2/3 minus 1 plus 1/2 plus 1/√3 0 minus 1/2. So this was the primary ladder. J equals 3/2. This was the secondary ladder. J equals 1/2. And so some of the features that we discussed were the orthogonality of these states to those states. Even though they have the same value of Jz, they're orthogonal because they correspond to different values of total angular momentum J. We also discussed that the values of the coefficients in the top half of the ladder, if I draw a line here, the coefficients above and below that line for j, z equals 0 are related by parity symmetry. So we saw this coefficient is the same as this one, this coefficient is the same as this one. We can make a similar statement for the secondary ladder. If I draw a horizontal line through these guys, this coefficient is related to this one, but with a minus sign. This coefficient is related to this one also with a minus sign. There's a general rule that we can write down that will tell us whether the sign is +1 or -1 very easily, and that will cut our work in half, so that we only have to calculate the top half of the ladder, and then we can immediately infer what the bottom half of the ladder is. So to close out this example, it's useful to assemble these coefficients into a matrix. The coefficients are called the Clebsch-Gordan coefficients. I could write this matrix in a few different ways, but the one that's most compact and shows you these structures most clearly is the one where I group things based on JZ. So I'm going to put the state from the second ladder that also has JZ plus 1/2 right next to the state from the first ladder that has JZ plus 1/2. Right, so these are my JZ states. And I can write these as a giant matrix made out of the LZ SZ states. All right, so if I fill in the matrix, 3/2 is uniquely made out of +1 plus 1/2. That's 1, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0 down here. Likewise, 3/2, -3/2 is uniquely made out of -1, -3/2. So that's 1 down in this corner and zeros everywhere else. 6, okay. The 3/2 plus 1/2 state was made up of a combination of the next two, 1/√3 and √2/3. 0, 0. That same state JZ, but with the different value of J, was made up of the orthogonal combination of the same two states. So this one was √2/3, -1/√3, 0, 0. And this is nice because these guys form their own little block. These guys also form a block. √2/3, 1/√3, 1/√3, -√2/3. So the reason that they form blocks is because we chose to group the states based on this value of JZ. So this is one JZ block, this is another JZ block, and that corresponds to this set here. So this maybe makes it a little easier to see that you have one combination and the orthogonal combination for the two states of different J for the same value of JZ. Okay, this matrix can be written even more compactly in a table, which is one of the standard reference results that all physicists need to look up at some point in their lives. The table of Clebsch-Gordan coefficients is nicely calculated for you in Griffiths. If you have this textbook, it is page 188, table 4.8. I also have this directly in the notes, the PDF that I put on Canvas. So let me share screen momentarily. We'll talk about how to read that table. All right, everybody's seeing the PDF, yeah?
Yes.
Okay, so this was the PDF that I put online. If you scroll down, this is a screenshot of that table, the relevant table for the spin 1 plus spin 1/2 addition of angular momentum. I also have this link. So here's the page in Griffiths where you can find it if you have that textbook. In general, this is a link to the massive PDF, which has everything compiled into a summary sheet for particle physicists. This is that PDF. So this is the result of all possible angular momentum addition that you might ever need. The first several angular momentum values being added. Right now we're talking about this table, the spin 1 and spin 1/2 addition. So there's a lot of information contained in a very dense way in this table. Let me talk very briefly about how to read the table. If you look at the numbers in these gray boxes, these numbers are precisely the ones that we just wrote in our matrix. The values on the vertical columns here, so this 3/2 plus 3/2, that's clearly J equals 3/2, JZ equals plus 3/2. This tells you how to resolve that total J state into spin +1, LZ +1, and SZ +1/2. This coefficient is free. This state is uniquely made out of this one, so the factor is 1. So each of these little corners in the table describes the different values of JZ. These are the subspaces that we just wrote in our matrix. So this was the JZ plus 3/2 matrix. The JZ plus 1/2 matrix describes two possible ladders, J equals 3/2 and J equals 1/2. These coefficients here should look familiar. This is the coefficients in the block that we assembled in our matrix from our final answer. There's the 1/3, the 2/3, 2/3 minus 1/3. So the caveat on how to read this is every number inside this block is implied to have a square root on it. And if there's a minus sign, don't take the square root with the minus sign. The minus sign goes outside of the square root. So I don't know if you guys can see the camera at the same time that I have the screen being shared. But this 1/3, 2/3 is telling me that my state 3/2 plus 1/2 is made out of 1 over square root 3, root 2 over 3. That's this mapping of the coefficients. The other state plus 1/2 for JZ, 1/2 for the value of J was square root of 2/3 minus square root of 1/3. So this is how you read the ladder. This is this block described in that ultra compact table. This is the other block described in that ultra compact table. So I am making this reference available to you. There should be no mystery about what the answer should be for the Clebsch-Gordan coefficients. Deriving them yourself is maybe another exercise. So my plan is to give you on the homework assignment coming up 1 plus 1, or sort of spin 1 and angular momentum 1, so that you will construct this table and you can immediately compare and make sure you get the correct answers. Okay, any questions on how to read the tables that are standard calculations? All right, let me unshare screen so that I remember to go back. Okay.
You should probably pin your video for the recording.
Sorry?
You should on Zoom, you should pin your video for the recording.
I think the video is recording, yes?
Oh, but I think it's currently recording Joe's camera.
Is it? How do I know which one is recording?
But it's usually just the one you're seeing. So Dr. Cillian usually pins his video.
Ah, okay. That's probably why the video every once in a while swaps back to somebody else's.
Yeah.
Okay, thank you for that. Okay. So that was one of the simpler examples, spin 1 and spin 1/2 together. The other simplest example that I can give you is maybe a little too simple. This is the addition of two spin 1/2 states. So let's talk about spin 1/2 together with another spin 1/2. So we talk about it as if it's addition of angular momentum. We also write it as if it's a tensor product. So it's easy to get tripped up on the language there. So this would be something like spin 1 is 1/2, and I've got another spin number 2, which is also spin 1/2. And I want to add these things up together. So my picture is I start off with S1z equals plus 1/2, S1z equals minus 1/2. These are the allowed values for the first spin state. The second spin state can also be plus 1/2 or minus 1/2. So if I tally up what are my allowed states, I can have plus 1/2 plus 1/2. That's going to give me spin plus 1. This must be part of the ladder including jz equals minus 1 and jz equals 0. This original space was 2 times 2, 4-dimensional to start off with. This ladder of j equals 1 is 3-dimensional. So there's got to be one state left over. That one state left over is made of the opposite combination that gives me 0. I can go up and then down or down and then up. That's 2 different possibilities. So there's an extra dimension here, a singlet state at jz equals 0. So this is my 1D configuration. So when I break apart this group theory, having one spin 1/2 and another spin 1/2, this is going to resolve into a primary ladder, which is j equals 1, and a separate ladder, which is j equals 0, a lone isolated state. So this is the decomposition that we want to do. The strategy, as before, is to first construct the top state. The top state is unique. So I must have j equals 1, jz equals plus 1, is uniquely made out of the combination S1z is plus 1/2, S2z is also plus 1/2. For spin 1/2, where I've only got 2 states, this notation gets a little ridiculous. It's much more common and compact to just call this state something like plus plus, spin up, where this means plus 1/2, plus 1/2. So if my state 1 plus 1 is equal to plus plus, then I generate from that ladder, that same j equals 1 ladder, I generate the rest of the states by applying the lowering operator. So I will take this state and I will apply j minus to it in terms of total angular momentum j on the left-hand side, and in terms of spin 1 minus plus spin 2 minus on the right side. All right, so to remind ourselves, the formula that we use a billion times going through this is the value of the lowering operator. When the lowering operator acts on a state j, jz, it gives you back h bar square root j plus 1. This comes from the eigenvalue of j squared, minus jz minus 1. jz minus 1. And this is true no matter what kind of angular momentum I'm talking about. So when j minus acts on plus 1 plus 1, so this one gives me h bar square root 1 times 2, so that's 2, minus 1 times 0. So just square root of 2. 1, and then I lower the value of jz to 0. On the right-hand side, S minus is going to give me the same answer. I only have to calculate the coefficient once because they're both spin up. So I get h bar square root of, for this one, the spin is 1/2, so that's 1/2 times 3/2. That's 3/4 minus 1/2 times negative 1/2. So that's plus 1/4. And I get first lowering this first spin to minus. And then I have an identical calculation to get the coefficients for the second one, plus minus. So this square root is, of course, just 1. Cancel the h bars. And this gives me the state 1, 0 equals 1 over square root of 2 plus minus plus 1 over square root of 2 minus plus. The fact that I get a relative plus sign in here is guaranteed from the start because the total angular momentum was always the sum of the first angular momentum and the second angular momentum. So it's no surprise that whatever coefficient I get, I have a plus sign here for this first ladder. We can guess immediately that the unique lowest state of this ladder is just going to be given by minus minus with a positive 1 for the coefficient, but we can double check that by again applying the lowering operator. All right, on the right-hand side, life is even easier because when I try to lower the spins, there's only one of them that I can lower. If spin number 2 is already spin down, I can't lower it again. So the only contribution that I get is from lowering the one that's spin up. On the left-hand side, if I plug in this formula, I get h bar square root, that's 1 times 2 minus 0. So I get 1 minus 1. Equals, on the right-hand side, I had 1 over root 2. This S1 minus can only lower this state. It gives me 0 when it tries to act on that state. That coefficient is again 1. For the same reason that it was 1 here. Likewise, when I have S2 minus, that gives me 0 when it acts on the first cat. It only gives me something non-zero when it acts on the second cat. So I get plus 1 over root 2 h bar minus minus. These two terms are the same. This is just equal to square root of 2 h bar minus minus. And I cancel my coefficients, and you get what you expect. So this generates all 3 states in the spin 1 ladder. The last step is to find the orthogonal combination that makes up the spin singlet state. That is the orthogonal combination to this one, and it's easy to look at it and read off the answer immediately. So we know that the spin 0 state, 0, 0, is in general some combination of alpha plus minus plus beta minus plus. We require orthogonality. That the state 0, 0 must be orthogonal to the state 1, 0. So this tells me alpha over square root of 2 plus beta over square root of 2 equals 0, as well as the normalization condition alpha squared plus beta squared equals 1. And this uniquely tells me up to an overall sign that I must have alpha equals 1 over root 2, beta equals minus 1 over root 2. You have some flexibility in which one you choose to be positive, which one you choose to be negative. Conventionally, you pick the first coefficient to be positive where that first spin is maximized. So this gives me the singlet state 0, 0 is 1 over root 2 plus minus 1 over root 2 minus plus. I can conveniently summarize the results in matrix form the same way we did before. So I have 1 plus 1, 1, 0, 0, 0, 1 minus 1. These are my JZ states expressed in terms of plus plus. This is S1Z, S2Z, plus minus, minus plus, minus minus. And we got 1, 0, 0, 0, 0, 1 over root 2, 1 over root 2, 0, 0, 1 over root 2, minus 1 over root 2, 0, 0, 0, 0, 1. And again, written in this form, the matrix nicely separates out into blocks. These blocks corresponding to the subspace, JZ equals 0, JZ equals plus 1, JZ equals minus 1. And if I go back and again momentarily share screen, you read this off and compare it with the table of Clebsch-Gordon coefficients, and you see that we got the right answer. That's 1, 1 over root 2, 1 over root 2, 1 over root 2 minus 1 over root 2, and 1. All right, these are the two simplest examples that you can add up angular momentum with. We've done 1/2 plus 1/2, 1 plus 1/2, and then for homework I will have you do 1 plus 1. Any questions on these specific examples before we talk about the problem more generally? Okay. Stopping share screen. Good, I am still in, thank you for that. Okay, to repeat the general procedure in words. So if you have two spins that you're adding together, you've got one spin state which has angular momentum J1, angular momentum component J1Z, and you're combining that together with another state or another degree of freedom that has total angular momentum J2, Z component J2Z, and you're translating this to the total angular momentum states J and JZ. Step one is find the biggest ladder, find the primary ladder. Your starting point is the statement that the top state is unique. So the state J equals J1 plus J2, the maximum possible total angular momentum I can form, whose Z component JZ is equal to J, that complete maximum state. This state can only come from the combination J1 plus J1, J2 plus J2. The notation gets a little bit weird. But I think you understand conceptually what I was showing you multiple times before, that the maximum state of the ladder, where JZ is maximized and total angular momentum is maximized, can only come from the state where J1 is all the way up, J2 is also all the way up. That forms the maximum state of the ladder. Once you have this, you generate the rest of the ladder using the lowering operator. That operator is J minus equals, let's call it J1 minus plus J2 minus, lowering on the total ladder, lowering on each ladder separately, which satisfies J minus J, JZ equals H bar square root J, J plus 1 minus JZ, JZ minus 1. You can repeat this to generate the entire ladder by brute force, or you can shortcut and only calculate half of it and immediately infer the lower half of the ladder with parity. So that general rule, it could change sign or it could have the same sign. So if I compare the matrix element J1, J1Z, J2, J2Z, overlap with J, JZ, right? So this is writing the total state J and JZ as a component projected onto definite J1Z and definite J2Z. I want to compare this, it's -1 to some number, which I will write down in a moment, compared to the matrix element where I flip all of the Z components. Flip this one, flip that one, flip this one. So I'm relating this to J1, negative J1Z, J2, negative J2Z, J, negative JZ. So if I flip all of the Z components of everything, I get either +1 or -1. And that number that determines whether you get +1 or -1 is J minus J1 minus J2. So it's controlled just by the total angular momentum involved when you're talking about that total angular momentum, that total angular momentum, and this one. So this will determine whether you have even parity and the sign is +1, or odd parity and the sign is -1 when you reflect from the upper half of the ladder to the lower half of the ladder. All right, once you have found the complete first ladder, you have found the biggest ladder all the way down, now you need to find the second ladder. The key is that the top state of the second ladder must be orthogonal to the second highest state in the first ladder. So you start off by finding the orthogonal combination from the first ladder. So what I mean by this is, if in the first ladder, your top state was J plus J equals plus J1 plus J2. Right? Everything is maximized. That second state, still total spin J, but now total projection J minus 1. This is some combination where you lowered each of these values by 1. So this is some alpha J1 minus 1, J2 plus beta J1, J2 minus 1. This is some combination of those two states. The top of the second ladder is orthogonal to that. This is J minus 1 plus J. They both belong to that JZ subspace. They have the same component. Plus J minus 1. Yeah, so both the top state of the second ladder has JZ equals J minus 1. And the second state from the first ladder also has JZ minus 1. They are the opposite combinations of each other. So once you have found the first ladder, you can take the orthogonal combination to form the top rung of the second ladder. You have some freedom in the coefficients. You can always choose the coefficients to be real. They must always be normalized to 1. And conventionally, we choose the coefficient here sort of labeled alpha, the one where the first spin is maximized. Choose that one to be positive. Once you found the top state of the second ladder, you can rinse and repeat. Use the lowering operator over and over again, parity symmetry when you get halfway down, and you construct the entire second ladder. Once you found the second ladder, if there's more ladders left over, if you haven't exhausted all of the degrees of freedom, then you need to find a third ladder. You will take the next state down, the third state from the first ladder, and the second state from the second ladder. And you need to find a third combination that is orthogonal to both of them. And you will keep doing this. This will generate more and more ladders until you exhaust the entire vector space. This one must be orthogonal to both of the first two. And then as before, you lower the state with J minus. Repeat until you have exhausted all of the representations of the vector space. So if I try to draw a picture associated with this, the overall result looks like this. I have the biggest ladder, which has J equals J1 plus J2. And I've got a whole ladder of states. J plus J, J plus J minus 1, J plus J minus 2, on down the line. The ladder is symmetric, so it goes down to negative J minus 2, negative J minus 1, and terminates at negative J. So this is my primary ladder. This is my maximum combination of J's. If I have a secondary ladder, that secondary ladder is smaller than this one. This has J equals J1 plus J2 minus 1. one less unit of angular momentum. This state will have j minus 1. Let me just call it j, I guess, since I've labeled it up here. Plus j plus j minus 1, j minus 1, j minus j. If I have a third ladder, I have j equals j1 plus j2 minus 2. This one is smaller than the one that came before. So this is j plus j, j minus j. And I can have as many ladders as it takes to use up all of the vector space. To go from one rung of the ladder down to the one below it, I use j minus. To find a new ladder after I found the one before it, I require orthogonality. This combination must be orthogonal. All of these combinations must be orthogonal. And in this way, starting with the biggest ladder and then exhaustively pulling out all of the states, you fill out all possible representations of the angular momentum. Some terminology, these are referred to as irreducible representations. Each ladder that we can construct is completely independent from all of the other ones. So the statement is, when I add up angular momentum, the combination of two angular momenta is reducible. I can separate that out into one total ladder, which is irreducible, a second total ladder, which is also irreducible and orthogonal to the first one, and so on. So this is what it looks like when we do things like 1 times 1/2 equals 3/2 plus 1. And 1/2 times 1/2 equals 1 plus 0. It's this kind of decomposition into a series of ladders. All right, any questions so far? Okay, I don't want to sink too much time into this, but I want to say a few words about the case of having general orbital angular momentum L together with spin 1/2, because that's a combination that arises very frequently. So I have some general ladder of orbital angular momenta. I have LZ equals plus L, minus 1, minus 2. And then on top of this angular momentum ladder, I have spin 1/2. So I can split it up or down. Plus 1/2, minus 1/2. You get the idea. So this is going to split into two ladders. Let's do the counting for the number of states. When I have L angular momentum, how many states are in this ladder? I go from plus L to minus L. through 0. 2L plus 1. So when I have L times 1/2, in this vector space, I have 2L plus 1 states times how many states are in the spin 1/2 ladder? Just 2. So the total vector space that I start off with in this composite ladder is 4L plus 2 dimensional vector space. When I split this up, I'm going to get 2 ladders. The maximum ladder, the primary ladder, is going to have L plus 1/2. So I'm going to split this off into L plus 1/2 is the maximum primary ladder. The number of states in this ladder is 2 times L plus 1/2 plus 1. So this is 2L plus 2 states. I also have a secondary ladder. That first ladder is L plus 1/2. The second ladder is L minus 1/2. That's made up of that same value of LZ, and it's orthogonal to this first one. The number of states in this ladder is 2L minus 1/2 plus 1, and that's 2L. So if I compare the dimensionality, I'm splitting my 4L plus 2 dimensional ladder into the primary 2L plus 2 dimensional ladder and a secondary 2L dimensional ladder. That exhausts the full vector space. So there are exactly 2 ladders that I can make out of this, one having L plus 1/2, one having L minus 1/2. So we can do the whole song and dance that we just set up in general. But in this case, since there's exactly 2 states at every level, we can take a shortcut. All right, so the statement is there are 2 possible values of JZ. This splitting takes LZ and it splits it into LZ plus 1/2, LZ minus 1/2. To say it the other way around, if this is JZ, then that value of JZ can either have come from LZ spin up, or it can have come from L plus 1 minus 1/2. So I don't know if that cartoon makes sense to you. What I'm trying to say mathematically is that the state where I have J equals L plus 1/2, that's the state on the primary ladder, and a given value of JZ is made up of some combination of the lower value of L spin up and a higher value of L spin down. And I have to add them both up in a way that gives me JZ. So this has L equals LZ equals JZ plus 1 spin down. Is that the convention that I have in the notes? Let's switch this around. All right, let me make sure I'm not changing course of bit string here. LZ equals JZ minus 1/2 spin up plus beta LZ equals JZ minus 1/2 spin down. Okay, sorry about that. So I can add up the total value of JZ by having a lower value of L spin up or by having a higher value of L spin down. Okay. Sorry, now I got this right. JZ minus 1/2 in the first state, spin up, gives me total JZ. JZ plus 1/2 in the second state, spin down, also gives me JZ. And I know the state in the primary ladder with this value of JZ is made up of some combination of those 2 states. The state in the secondary ladder, L minus 1/2, with the same value of JZ, is made up of the same 2 states, but an orthogonal combination of them. So for a given value of jz, there are 4 unknown coefficients. And I immediately know 3 relations between them. I have to have normalization for each one separately. So I have to have alpha squared plus beta squared is 1, and alpha prime squared plus beta prime squared equals 1. And I have orthogonality. So I have alpha prime plus beta prime equals 0. 4 unknown coefficients, 3 relations I get for free. You only actually have to calculate one thing to completely fix all of the values. So for instance, this gives me alpha prime over beta prime automatically is negative beta over alpha. And similarly, I can write beta is 1 over square root 1 plus alpha squared over beta squared, and so on. So I only really need to calculate one thing. Calculate, say, the ratio alpha over beta. I can fix this coefficient by just acting on it by j squared. I need to figure out which of these combinations gives me j equals L plus a half, which one gives me j equals L minus a half. So to do this, you act on the states with j squared. So this is L vector plus S vector squared, which is L squared plus S squared plus 2L dot S. Which is L squared plus S squared plus 2LZSZ plus 2LXSX plus LYSY. These guys do not commute, they do not play nicely in terms of SZ and LZ. It's advantageous to trade them out in favor of L plus and L minus, and S plus and S minus. So we use, for instance, Lx is 1/2 L plus plus L minus. And Ly is 1 over 2I, L plus minus L minus. And you have a similar relationship for S plus and S minus. So when I plug these relations in, I get j squared equals L squared plus S squared plus 2LZSZ plus L plus S minus plus L minus S plus. So for instance, I can take this expression now and I can act with it on the state J equals L plus 1/2 JZ and write it in this long form, L squared, S squared, 2LZSZ, L plus S minus, L minus S plus, acting on the state we wrote down. Alpha LZ equals JZ minus 1/2, spin up, plus beta LZ equals JZ plus 1/2, spin down. I'll spare you the algebra. Suffice to say that if I act with j squared on this, I know exactly what I get. I return a value that depends on L plus a half, right? On this side, I know how to act with L squared, S squared, LZ, and SZ. Each of these things is well defined on the right-hand side. When I impose this condition, Let's see, so again, you have something simple, right? Like this one, which is already spin up, you can't raise the spin again. So this term is 0 when acting on this state. This term acting on it lowers that state. And it gives me something in terms of JZ minus 1/2 minus. And so on. So by imposing these conditions, I get something on the left-hand side in terms of the state here, and then something on the right-hand side. The algebra is on the notes online. Suffice to say that when you work out all of the algebra, this is the answer you get. And with this, you can plug it back in and you can write the full answer for the decomposition of the states. So there's an overall normalization factor, 1 over square root of 2L plus 1. And then I get plus or minus depending on which of the two ladders I'm talking about, the primary or the secondary ladder. So there's a relative sign in front here. This is square root L plus 1/2 plus or minus JZ. This one is L plus 1/2 minus plus JZ. So these things are normalized, they add up to 1. There's a relative sign between them so that the two ladders are orthogonal. And I build the general state with arbitrary JZ in either ladder out of the appropriate combination of larger value of L spin down, smaller value of L spin up. I don't have something that I immediately want you to do with this formula, but this is one that arises very often when you need to add angular momentum. So I thought it was important to show you the solution for this. In the notes online on Canvas, I worked through all of the algebra that leads to this result if you want to see it. All right. In the remaining 15 minutes, I want to give you a flavor of a subject that is fairly abstract and esoteric, but it's at the origin of a lot of selection rules in quantum mechanics, which is the idea that there are operators that carry finite amounts of angular momentum. We've been talking about angular momentum associated with the states. So if I have a state with some value of angular momentum, and then I act on it with an operator, if that new state after I act on it transforms with a different amount of angular momentum, then that means the operator that you acted on with has added angular momentum to the state. So what I mean is, if I have a state LLZ with well-defined angular momentum, and I act on it with some operator O, this thing is a new quantum state. I can ask how that quantum state rotates. If this quantum state rotates differently than that one, then the operator O has delivered some amount of angular momentum to the state. So I want to try and make more precise this notion of how much angular momentum an operator is delivering. So this is related to statements like the photon has 1 unit of angular momentum. What that means is that when you put in the Hamiltonian an interaction with an electromagnetic potential, that vector potential imparts, that operator imparts one unit of angular momentum. And we want to define what that means. So specifically, the result that I want to show, I want to show that a vector operator of any kind carries 1 unit of angular momentum. So that with a vector operator, you can associate L equals 1 as if it were a quantum state of its own. So this is similar to what we already saw when we discussed spin. We saw that if I had a state, a quantum state that is a vector, psi x of r, psi y of r, psi z of r. When we worked out how this state transforms, we said that this quantum state has L equals 1. Vector wave function had L equals 1. That was related to the fact that there were 3 components that get mixed up under rotation. 3 components form a 3-state ladder. The 3-state ladder is L equals 1. Ultimately, it's the same reason why a vector operator can be associated with having spin 1. All right, so the heart of it is how a vector transforms. Under rotations, the 3 components of the vector get scrambled up. If I take the rotation operator, u dagger of theta, and I act on my vector vi, ith component of the vector v, this was how the operator transformed, sort of Heisenberg representation, u dagger v u. This was equal to the rotation matrix R of theta ij vj. So on the left-hand side, this is the unitary quantum transformation of how the operator rotates. On the right-hand side, this is the regular rotation matrix, like a 3x3 matrix with cosines and sines in it, that mixes up the 3 components of V. If I take this general transformation and I expand for infinitesimal transformations, so I know the unitary operator u of theta is e to the minus I over h bar j dot theta. Likewise, I can also expand the rotation matrix on the right-hand side, Rij of theta. Right, so this is, for small rotations, this is 1 minus I over h bar j dot theta, plus order theta squared corrections. Likewise, this is given by Kronecker delta ij minus sum over k epsilon ijk theta k plus ordered theta squared corrections. If you plug in both of these expansions into this formula, you translate this statement about how the vector rotates into a statement about its commutation algebra. So this is equivalent to commutator of the vector operator vi with j sub j is I h bar sum over k epsilon ijk v sub k. This looks very similar to the angular momentum commutation relations. That is, of course, because angular momentum is the generator of rotations. So when I plug this in, this says a general vector gets rotated like an angular momentum does. So this is what the rotation properties look like in Cartesian coordinates. We want to ask the question in spherical coordinates. How do the L and LZ values associated with spherical harmonics transform? So we want to translate this algebraic statement into a similar one about total angular momentum and spherical harmonics. So again, there are some highly abstract terms that are associated with this. I want to tell you what they are, but don't get bogged down in the terminology. These are sometimes referred to as Cartesian tensors. The vector is a rank 1 Cartesian tensor. It has Cartesian components x, y, and z. You can make similar statements about matrices that have 2 components to them, or higher rank tensors. The important part here is that these are Cartesian components. We are now translating those into spherical tensors. I.e., written in spherical harmonics or spherical coordinates. So the analogous statement that we want to make in terms of the angular momentum space is if I have an operator that transforms in the following way. Operator O with a well-defined total angular momentum index L and a well-defined Z component of angular momentum index M. Under a transformation, it rotates like the angular momentum states do. None of this like detailed derivation is going to be on the test. Don't panic about that, but I want you to understand where this comes from. So this is a similar statement about the rotations in spherical coordinates. I'm transforming some operator and claiming that this operator has well-defined total angular momentum L and Z component M if it rotates among those components the same way the angular momentum states do. It has well-defined total angular momentum L because it takes that state and it rotates it into other states that also have angular momentum L. If I had different values here, then this operator would not have well-defined total angular momentum L. Under rotations, the only thing that it does is it scrambles up the Z component. So it can mix up M and M prime, and I can mix up for the same values of L, the different Z components M and M prime. That's the physics of what this statement is saying. All right, just the last 5 minutes. Okay, suffice to say that I can do the same exercise. If I expand this relation now for infinitesimal transformations, I again get a set of commutation relations. So what this tells me is that Ji with this operator OLM is sum over M prime OLM prime times the matrix element of angular momentum LM prime Ji LF. So in operator language, the commutator is what tells you how the operator transforms. Commutator with OLM should transform like matrix elements of the angular momentum. So if I take I equals Z, the Z component is special, that's related to this value M. For JZ, that matrix element is simple. LM prime JZ LM. This is an eigenstate of Jz. This is just M H bar. And then these states are orthogonal. They're orthonormalized. So this is M H bar delta M M prime. So under commutation with Jz, an operator which has well-defined Z component of angular momentum should look like it has an eigenvalue, M H bar. O L M. I could write this out similarly for X and Y, but X and Y are not good choices when I'm talking about Jz. X and Y are better rephrased in terms of plus and minus, which are just linear combinations of X and Y. For J plus minus, that matrix element is again simple. This gives me H bar square root L plus 1 minus M minus plus 1 times delta L prime, delta M prime, M plus or minus 1. So this defines what I mean by raising or lowering that component. So this tells me that I sort of have a ladder of operators, the same way I have ladders of states that are related by different Z components of angular momentum. J plus minus OLM equals H bar square root L plus 1 minus M plus minus 1. Sorry, this is plus minus minus 8. All right, so these two relations are sort of the operator version of what raising and lowering angular momentum does to states. Instead of having these operators act on a quantum state, they are commutators with the operator in question. But it looks quite analogous. So I'm out of time. I have to stop here. Next class, I will finish up the implications of this. With this, I want to take this and apply it to the vector operator. And we will find that Vz is an eigenvalue with well-defined Z component. The X and Y components of a vector, you have to take circularly polarized combinations. You'll have vector X plus or minus I vector Y. Those combinations of any vector will have well-defined angular momentum values, plus 1 or minus 1. So by doing that, I can take any operator and using these commutation relations, split them up into what their angular momentum components are. This is important because when we talk about matrix elements in perturbation theory, often we will have Hamiltonians that bring in vector operators. So something like the electric dipole moment transition. That's something where you have an external electric field dot product with the position vector. The position vector is a vector operator in this sense. That is the reason why that Hamiltonian, which is the driving transition in atoms, will change the angular momentum value by 1 unit, because that vector operator carries 1 unit of angular momentum. That is what I mean when I say that the photon has 1 unit of angular momentum, and that the atom transitions by emitting or absorbing a photon. Okay, I will leave this here and we will finish the rest of this derivation next time, and then we will move on to discussions of the hydrogen atom. Thank you guys very much. Have a nice weekend.
Thank you, Professor.
Thank you.